Welcome back to Cosmos in a Pod Space and Astronomy series. When we look up at the night sky, it's easy to think of stars as just these tiny twinkling points of light. But the reality is way more spectacular. Today's deep dive is all about uncovering the mind-blowing diversity of stars that fill our universe.
It really is a cosmic zoo out there. Everything from tiny, cool red dwarfs that could outlive our galaxy
Right?
to colossal supergiants that blaze with the intensity of millions of suns.
Wow, millions of suns. Okay, I am hooked already. So how do astronomers even begin to make sense of this incredible variety? Where do you even start when you're trying to categorize stars?
It is a challenge for sure, but astronomers are clever folks. They've come up with a system that's like a stellar fingerprint analysis. It's called the Morgan-Keenan classification system, or MK for short.
MK. So
Yeah.
that's how they keep track of all these stellar suspects, huh? What's the secret behind this MK system?
Think of it like this. Every star emits light, right? And that light carries a unique signature, a spectrum that tells us a lot about the star's temperature, chemical composition, and even its motion.
So it's like a star's personal ID card encoded in light. That's pretty cool.
Exactly. And this MK system uses these spectral clues to sort stars into different categories, each designated by a letter.
Okay, spill the beans. What are these stellar categories?
Get ready for a cosmic alphabet soup. O, B, A, F, G, K, and M. And just to make it easier to remember, there's this handy mnemonic, "Oh, be a fine girl, guy, kiss me."
Huh. That's definitely one way to remember it. So is this sequence telling us something about the stars themselves?
It absolutely is. It's essentially a temperature scale, from hottest to coolest. At one end of the spectrum, you have the O-type stars, the hottest and most massive. They're burning with such intense energy that they glow with a brilliant blue-white light. Their surface temperatures can exceed a scorching 30,000 Kelvin.
30,000 Kelvin. Wow,
Yeah.
that's hot. Can you even imagine?
Right. And then, as you move down the spectral ladder, things start to cool down. We pass through the B-type stars, then A, then F, each getting progressively cooler and changing color.
So like the colors of a rainbow, but in stars.
Exactly. It's a beautiful spectrum, really. And finally, at the cooler end, we reach the M-type stars. These are the red dwarfs we talked about earlier, and they're much more laid back than their hot blue cousins. Their surface temperatures can be as low as 3,000 Kelvin.
That's still incredibly hot, but it's definitely a far cry from 30,000 Kelvin. So where does our sun fall on this cosmic temperature scale?
Well, our sun is a pretty average star. It's a G-type star, comfortably nestled in the middle of the spectral sequence. With a surface temperature of around 5,800 Kelvin, it's not too hot, not too cold, just right for supporting life on Earth, as far as we know.
Goldilocks approved. So we have this whole spectrum of stars, each with its unique characteristics. Where do we go from here? What are some of the most intriguing types of stars out there?
Well, if you're looking for the most common star in the universe, look no further than the humble red dwarf. These cool, faint stars make up something like 70 to 80% of all stars in our galaxy.
Wow, that many. So they're kind of like the cosmic underdogs, quietly dominating the stellar population.
Exactly. And what's really fascinating about them is their incredible longevity. They burn their hydrogen fuel so slowly that their lifespans can stretch into trillions of years. That's thousands of times longer than our sun's expected lifetime.
Trillions of years. That's mind-boggling. So they're like the tortoises of the cosmos, slowly and steadily shining for eons.
That's a perfect analogy. And this incredible longevity has some really interesting implications, especially when we think about the possibility of life on other planets.
Ooh, intriguing. Why would their long lifespan matter for life?
Think about it. On Earth, it took billions of years for life to evolve from simple microbes to complex organisms like us. If a star lived only a few million or billion years, it's unlikely that life on its planets would have enough time to reach that level of complexity.
Ah, that makes sense. So red dwarfs, with their incredibly long lifespans, could provide the stable environments needed for life to really take hold and flourish. That's pretty cool.
It is. And there's growing evidence to support this idea. We've discovered planets orbiting red dwarfs, some even within the habitable zone where temperatures could allow for liquid water, a key ingredient for life as we know it.
So these seemingly insignificant stars might be holding the keys to unlocking the secrets of life beyond Earth. I love that.
It's certainly a possibility. And it just goes to show that we shouldn't judge a star by its size or brightness. Even the smallest and faintest stars can hold incredible secrets.
That's a great point. But what about stars like Our sun, where do they fit into this cosmic picture?
Well, our sun, along with a good chunk of the stars you see in the night sky, belong to a category called main sequence stars. These stars are in the prime of their lives, you could say.
Prime of their lives. What does that mean for a star?
It means they're busy fusing hydrogen into helium in their cores, releasing vast amounts of energy in the process. This is what makes them shine so brightly.
Ah, so they're the cosmic powerhouses. The ones keeping the lights on in the universe.
Exactly. And they come in a range of sizes and temperatures, all following this pattern of hydrogen fusion. Our sun, as a G-type main sequence star, is kind of middle of the road in terms of temperature and size.
So we're not the most dazzling star in the galaxy, but we're getting the job done.
That's the way to look at it. And remember, main sequence stars, like our sun, are incredibly important because they're stable. They provide the long-term energy and stability that planetary systems like ours need to exist.
Right, because without that stable energy source, we wouldn't be here having this conversation. But I imagine there are stars out there that are a bit more dramatic. What about those stars that really grab our attention with their sheer size and brilliance?
Ah, yes, you're talking about the giants and supergiants of the cosmos. These are the stars that have graduated from the main sequence and are entering a new, more flamboyant chapter of their lives.
Flamboyant. That sounds exciting. Tell me more about these stellar celebrities.
Well, first we have the red giants. These are stars, often similar in mass to our sun, that have exhausted most of the hydrogen fuel in their cores. As they start to fuse helium, they undergo a dramatic transformation.
Dramatic in what way? What happens to them?
They begin to expand, and I mean really expand. They can swell up to hundreds of times their original size. Think of it like a balloon inflating, and as they expand, their surface cools down, giving them that characteristic reddish hue.
So they're like giant glowing orbs in space. I can see why they grab our attention.
Exactly, and one of the most famous examples of a red giant is Betelgeuse, the bright red star in the constellation Orion.
Betelgeuse. I've definitely heard of that one. It's amazing to think that a star we can see with the naked eye is going through such a dramatic transformation.
It is. And when we look at Betelgeuse, we're seeing a glimpse into our sun's future. In about 5 billion years, our sun will also become a red giant, expanding and engulfing the inner planets, including Mercury and Venus.
Whoa. That's a little scary to think about, but also incredibly fascinating. So, red giants are pretty impressive, but I bet the supergiants are even more mind-blowing.
Oh, you have no idea. Supergiants are the true heavyweights of the cosmos. They're formed from stars at least 10 times more massive than our sun.
10 times more massive. That's already huge. And what happens when these monsters run out of fuel?
Well, get ready for this. They expand to truly colossal sizes, sometimes exceeding 1,000 times the radius of our sun.
1,000 times the radius of our sun. That's like unimaginable. It must take an insane amount of energy to power a star that big.
It does. Supergiants are incredibly luminous, shining with the light of millions of suns. They're the rock stars of the universe, burning bright and living fast.
Burning bright and living fast. Is that why we see them so clearly in the night sky?
That's part of it, but it's also because they're relatively rare. Their intense energy output comes at a price. They burn through their fuel at a much faster rate than smaller stars, so their lifespans are much shorter. Only a few million to tens of millions of years, astronomically speaking.
Wow, so they're like the cosmic fireworks, putting on a spectacular show, but fading away much more quickly. It's amazing how diverse stars can be. So we've got red dwarfs, main sequence stars like our sun, and these incredible giants and supergiants. What happens next in a star's life? Where do they go from there?
That's where things get even more interesting, but I think that's a story for another part of our deep dive.
You're killing me. But, okay, I guess we have to leave our listeners in suspense for a bit. Don't forget to follow and subscribe to Cosmos in a Pod and our YouTube channel for more cosmic adventures. We'll be back soon to explore the final chapters in the lives of stars, and trust me, you won't want to miss it.
All right, so last time we left you on a cliffhanger. We talked about how stars evolve from those humble red dwarfs to those dazzling supergiants. But as with all things in the universe, even stars have an expiration date.
And I am ready to learn about the grand finale. So, what happens when a star runs out of fuel? Is it lights out, game over?
Not necessarily. It's not a simple off switch. The way a star ends its life depends a lot on its starting mass.
Okay, so like a cosmic weight class. Tell me more.
Exactly. Let's start with the stars that are up to 8 times the mass of our sun. When they reach the end of their main sequence lives, they start to shed their outer layers, like a snake shedding its skin.
A cosmic molting. That's a pretty vivid image. What's left behind after this stellar striptease?
What remains is the core of the star. A super dense, Earth-sized ball of matter called a white dwarf.
A white dwarf. So it's not really a star anymore.
Well, it's a stellar remnant. It's no longer generating energy through fusion, but it's still incredibly hot, glowing with leftover heat. Imagine squeezing the mass of the sun into something the size of our planet.
That's incredible. So dense. What eventually happens to a white dwarf? Does it just fade away?
Over billions of years, yes, it will slowly cool down and dim, eventually becoming a cold, dark object known as a black dwarf.
So a quiet ending for some stars. But what about the stars that are more than 8 times the mass of our sun? I have a feeling their grand finale is a bit more explosive.
You are absolutely right. These massive stars go out with a bang. Literally, we're talking about supernovae.
Supernovae, those are the incredibly bright explosions we sometimes see in distant galaxies, right?
Exactly. As a massive star runs out of fuel, its core collapses under its own immense gravity. This collapse triggers a shock wave that rips through the star, blasting its outer layers into space with incredible force.
So it's like a cosmic implosion that leads to a massive explosion. It's hard to even wrap my head around the scale of these events.
It is. And what's left behind after a supernova depends on the initial mass of the star. For stars that are, say, 10 to 20 times the mass of the sun, the core collapses into an incredibly dense object called a neutron star.
I've heard of neutron stars. They're like the ultimate cosmic oddities, right?
Absolutely. They are some of the most extreme objects in the universe. Imagine a sphere only about 10 to 20 kilometers across that's smaller than a city but packing in more mass than our entire sun.
Wait, a city-sized object with more mass than the sun? How is that even possible?
The gravity in a neutron star is so strong that it crushes the matter inside, forcing electrons and protons to combine and form neutrons. This creates a super dense material that's unlike anything we find here on Earth.
So it's like a giant atomic nucleus. I'm starting to understand why they call them neutron stars.
You got it. And just to get a sense of how extreme these objects are, imagine taking a teaspoon of neutron star material. That tiny amount would weigh billions of tons.
Billions of tons. Okay, that's officially mind-blowing.
Oh.
But what about the most massive stars, the ones that are much bigger than 20 times the mass of our sun? Do they also form neutron stars?
That's where things get even weirder. When these supermassive stars explode as supernovae, their cores collapse so completely that they form black holes.
Black holes. I think everyone has heard of black holes, but they're so hard to grasp. What exactly are they?
Imagine a region of space-time where gravity is so intense that nothing, not even light, can escape. That's a black hole.
So it's like a cosmic trapdoor. Anything that gets too close disappears forever.
You could think of it that way. And what's even crazier is that black holes warp the fabric of space-time around them. It's like dropping a bowling ball on a trampoline. The fabric stretches and distorts around the massive object.
Okay, that's helping me visualize it a bit better, but it's still pretty mind-boggling. So we have white dwarfs, neutron stars, and black holes, these remnants of dead stars. But I feel like we've skipped over some other intriguing types of stars. What about variable stars, for example?
Yes. Variable stars are fascinating because they change in brightness over time. They're not just steadily shining, they pulse, flicker, and sometimes even erupt.
So they're like the cosmic flashers of the universe. What causes this variability?
There are many different types of variable stars, and their variability can be caused by a range of factors. Some stars pulsate because of internal processes, like changes in their temperature or pressure. Others might be part of a binary system where two stars orbit each other, and their brightness changes as they eclipse each other.
So it's like they're putting on a celestial dance, changing their brightness as they interact.
That's a great way to put it. And these variable stars are not just pretty to look at. They're incredibly valuable tools for astronomers.
Tools? How so?
Well, one type of variable star, called a Cepheid variable, has a special relationship between its pulsation period and its luminosity. Basically, the longer the pulsation period, the brighter the star.
So it's like a cosmic clock that also tells us how bright the star is.
Exactly. And knowing a star's luminosity allows astronomers to calculate its distance from Earth. This is incredibly useful for mapping out the vast distances in the universe.
So by studying these blinking stars, astronomers can measure the vastness of space. That's pretty clever.
It is. And there are other types of variable stars like RR Lyrae stars that are useful for studying star clusters and the evolution of galaxies.
It's amazing how much information we can glean from these seemingly simple changes in a star's brightness. It's like they're sending us coded messages about the universe.
And then we have some truly unusual stars out there, like brown dwarfs and magnetars.
Brown dwarfs. Those are the failed stars, right?
Hmm.
The ones that never quite got massive enough to ignite nuclear fusion.
That's right. They're kind of like the in-betweeners of the cosmos. Not quite planets, not quite stars.
So they're like the cosmic teenagers, still figuring things out.
You could say that. And while they might not shine as brightly as stars, they're still fascinating objects to study. They can tell us a lot about star formation and the limits of stellar evolution.
I'm always up for learning about cosmic misfits. What about magnetars? Those sound intense.
They are. Magnetars are neutron stars with incredibly powerful magnetic fields, trillions of times stronger than Earth's magnetic field.
Trillions of times stronger. I can't even comprehend that. What makes their magnetic field so strong?
It's thought to be related to the way they form in supernova explosions. The rapid rotation and intense pressures within a newly formed neutron star can generate these extreme magnetic fields.
So they're like spinning cosmic magnets, but on a scale that's hard to even imagine.
Exactly. And these incredibly powerful magnetic fields can trigger some pretty wild phenomena, like bursts of high-energy X-rays and gamma rays.
So they're not just dense and heavy, they're also bursting with energy. I'm sensing a pattern here. The universe loves extremes.
It certainly does. And I think we have time for one more stellar oddity. Wolf-Rayet stars. These are massive hot stars that are in the process of losing their outer layers at an incredible rate.
Losing their outer layers. Is that similar to what happens when a star becomes a red giant?
It's similar in the sense that material is being ejected from the star, but with Wolf-Rayet stars, it's happening much more violently and rapidly. They have powerful stellar winds that are blasting material into space at millions of kilometers per hour.
Millions of kilometers per hour. That's like a cosmic hurricane. What causes these extreme stellar winds?
It's related to their intense radiation pressure. These stars are so hot and luminous that the pressure of the radiation is literally pushing their outer layers away.
So they're kind of like cosmic pressure cookers blasting their contents out into space.
That's a great analogy. And this process creates these beautiful and complex nebulae around Wolf-Rayet stars, where the ejected material glows with brilliant colors.
Okay, I think my brain is officially full. We've covered so much ground today, from the quiet deaths of white dwarfs to the explosive supernovae that give birth to neutron stars and black holes and all the weird and wonderful stars in between.
It really is a testament to the incredible diversity of the universe, isn't it?
It is. I'm starting to realize that every star has a story to tell, a unique journey through cosmic time. But with all we've learned today, I have to ask, are there still unanswered questions about stars? Mysteries that keep astronomers up at night?
Oh, absolutely. The universe is full of mysteries, and with every answer, we uncover new questions arise. But I think that's a story for next time.
You're killing me again with the cliffhangers. But, okay, I guess we have to leave our listeners wanting more. Don't forget to follow and subscribe to Cosmos in a Pod and our YouTube channel for the final part of our deep dives into the fascinating world of stars. We'll be back soon to explore those lingering mysteries and see what else we can discover about these celestial wonders. Welcome back to Cosmos in a Pod. I'm ready to delve into those stellar mysteries you mentioned. What are the big questions that have astronomers scratching their heads?
Well, one of the biggest puzzles is understanding the tipping point between a supernova forming a neutron star versus collapsing into a black hole. We know it has to do with mass, but the precise boundary is still a bit fuzzy. It's a delicate dance between gravity, nuclear forces, and the properties of matter under extreme pressure.
So, like a cosmic game of tug-of-war. Which force wins determines the fate of the star's core.
Exactly. And then there's the whole mystery surrounding black holes themselves. We can detect their gravitational influence, and we're starting to image them indirectly. But what truly lies at the heart of a black hole? It's a region where our current understanding of physics breaks down.
It's like peering into the abyss of the unknown. I imagine those questions are keeping theoretical physicists very busy.
They certainly are. And speaking of mysteries, how about the question of how planets form around different types of stars? We've discovered thousands of exoplanets, planets orbiting other stars, but the process of planet formation is still shrouded in, well, stardust.
Right. We know it involves gravity pulling together gas and dust.
Yeah.
But the specifics, how those materials clump together, how planets migrate within a system, there's so much we're still figuring out.
And it gets even more intriguing when we consider the diversity of stars themselves. Can planets form around red dwarfs with their intense flares? What about around massive stars that live fast and die young? Does the type of star influence the types of planets that can form and ultimately the potential for life?
So many questions. And speaking of life, That's probably the biggest mystery of all. Are we alone in the universe? Does life exist on other planets, orbiting other stars?
It's the ultimate question, isn't it? And while we haven't found definitive proof yet, the sheer number of stars and planetary systems out there makes the possibility incredibly exciting. Just think, billions of galaxies, each with billions of stars, many of which likely have planets. The odds seem to be in favor of life existing elsewhere.
It's both humbling and awe-inspiring to think about. And the more we learn about the diversity of stars, the more we realize how much we still don't know.
That's the beauty of science. It's a never-ending quest for knowledge. And the study of stars is a perfect example of that. It's a journey that takes us from the smallest particles to the largest structures in the universe.
So from atoms to galaxies, it's all connected. And what's amazing is that anyone can join this journey of discovery. You don't need a fancy telescope or a degree in astrophysics to appreciate the wonders of the night sky.
Absolutely. Just looking up at the stars can spark a sense of wonder and curiosity. It's a reminder of our place in the vastness of the cosmos, and it can inspire us to ask questions, to learn more, and to keep exploring.
Well said. And speaking of exploring, for those who want to dive deeper into the world of stars, what resources would you recommend?
There are so many great places to start. For getting to know the night sky, Stellarium is a fantastic free planetarium software that lets you explore the stars from your computer.
I've heard of that. It's like having a personal planetarium right on your screen.
Exactly. And for those who want a deeper dive into the science of stars, there are classic books like Cosmos by Carl Sagan and A Brief History of Time by Stephen Hawking.
Ah, yes, the greats.
Yeah.
Their books are truly inspiring, even for non-scientists.
And of course, you can always keep up with the latest astronomical discoveries through websites like NASA's website or by following science news outlets.
Great recommendations. It's so inspiring to see how much information and knowledge is out there for anyone who's curious about the universe.
And speaking of inspiration, don't forget to follow and subscribe to Cosmos in a Pod and our YouTube channel for more deep dives into the wonders of the cosmos. We have lots more exciting episodes coming up, covering everything from black holes to the search for extraterrestrial life.
That's right. We'll be exploring the mysteries of dark matter, the birth and death of galaxies, and so much more. So join us as we continue our exploration of the universe. This deep dive into the universe of stars has been absolutely fascinating. From their formation to their dramatic deaths, stars drive the evolution of galaxies, create the elements that make up our world, and inspire us to contemplate our place in the cosmos.
It's a reminder that we are all connected to the universe in profound ways. We are, after all, stardust.
A beautiful thought to end on. Thank you for joining us on this cosmic adventure. Until next time, keep looking up and keep exploring the wonders of the universe.